This is going to be our overview for the Unit 4 practice, both the pieces that were in our Chemistry 1 textbook, but also the pieces that were built in Canvas. So we're going to start with our page R67 problems. Number 217 and 218 were the problems that we were supposed to be working with to start. And the first one says identify the species in the equations that are Bronsted-Lowry acids and Bronsted-Lowry bases. So remember, our acids are going to be proton donors. Our bases are going to be proton acceptors. So if we look at part A, in this case, water on the other side of our arrow here is going to become hydroxide. So water has donated a proton and hydroxide has accepted it, or sorry, to create hydroxide. Cyanide accepts that proton. So water is our acid, cyanide is a base. But on the other side of the arrow, because this reaction is in equilibrium, we're going to have the opposite, their conjugate partners on the other side. So hydroxide is going to be our conjugate base, and hydrocyanic acid is going to be our acid. So it'll be acid, base, base, acid. Part B, again, we're looking before and after the arrow. HClO3 becomes ClO3 minus. So it has given up a proton. HClO3 is our acid. H2O is accepting that proton to become H3O plus, so H2O is a base. And then on the other side, ClO3 minus is a base, H3O plus is an acid, if we're looking at the reaction in the opposite direction. Part C, again, always look for that one proton difference, and you're going to be able to tell whether we've got an acid or a base. So again, we're starting off with our acid. Our hydroxide is a base. And then after the arrow, we have our conjugate base, and the water is our conjugate acid. Part D, HSO4 on the other side of the arrow becomes H2SO4. So it is accepting a proton, which means that HSO4 with the negative charge before the arrow is going to be a base. H3O plus is the acid. On the other side of the arrow, H2SO4 is our acid and H2O is our base. On number 218, which of the following are conjugate acid-base pairs? Remember, the difference is a proton. So if you look at part A, we have NH4 versus NH3. Or NH4 has our plus charge because it is an extra proton on our ammonia. Ammonia becomes ammonium. This is a conjugate acid-base pair. Looking at part B, H3PO4 and H2PO4 minus. Again, the only difference between those two is a single proton, so that is a conjugate acid-base pair. Part C, HSO4 and SO42 minus. Again, one proton difference there. They're both negative, but when we take that proton away, we end up with a double negative on that sulfate. So that is a conjugate acid-base pair. And then finally, we have H3O plus and OH minus. The difference between those two is 2 protons, so they are not a conjugate acid-base pair. 226 through 229 were the other parts of the assignment from page R67. So on 226, this is a stoichiometry problem. How many moles of sulfuric acid are required to neutralize 1.4 moles of potassium hydroxide? So on this one, you could make yourself a factor label grid. I'm not going to be able to draw this very well on a computer, but there's my factor label grid. Okay, so we would start off our problem again with what we're given. We're given 1.4 moles of potassium hydroxide. So that would go right here, 1.4 moles of potassium hydroxide. And then in our equation, we can see that 2 moles of KOH for every 1 mole of sulfuric acid. So we would have our mole ratio in order to cancel our starting value of 1.4 moles of potassium hydroxide. We put our 2 moles of KOH on the bottom for every 1 mole of sulfuric acid on the top. And then we can calculate and get our answer, which is 0.7 moles of sulfuric acid. On 227, we have a similar situation. We've got a stoichiometry problem, but we're pushing it a little bit further. What is the molarity of a hydrochloric acid solution if 25 milliliters of the solution reacts completely with 1.66 grams of NaHCO3? So that 1.66 grams is your starting point. We always start with what we're given in the question part of the problem. We would convert that into moles. We have to get to moles. We know that for every 1 mole of NaHCO3, we will have 1 mole of hydrochloric acid reacted. So if we can convert our 1.66 grams to moles by dividing by its molar mass of 84 grams per mole, we know how many moles of hydrochloric acid reacted because of that 1-to-1 ratio. The answer to that calculation is 0.0198 moles. 0.0198 moles of HCl was in 25 milliliters of the solution. Remember, molarity is moles per liter. So we can take our moles, we can divide it by this volume, but converted it to liters, and we will end up with 0.792 molar as our answer. Question number 228. In an acid-base titration reaction, how many milliliters of 0.180 molar HCl are required to neutralize 20 milliliters of 0.220 molar NaOH? This problem is not a stoichiometry problem. This problem is an M1V1, M2V2 problem. We have a molarity of one of our solutions, molarity of NaOH, 0.220 molar. We have a volume of that solution. So we have an M1 and a V1. We have a molarity of a different solution. In this case, our hydrochloric acid, 0.180 molar HCl. And we are looking for a volume. So we can use these as M1V1 for our base values and M2V2 for our acid, not knowing our V2. When we solve for V2, we're going to get 24.4 milliliters as our answer. 24.4 milliliters. Number 229, similar problem. How many milliliters of 0.456 molar, so 0.456 molar calcium hydroxide, we're looking for a volume. So these two go together. We don't know the volume, but that's an M1 and a V1. Okay. Are needed to neutralize 25 milliliters of 0.300 molar HCl. So we have one volume, we have two molarities. We can use M1V1 equals M2V2. Again, make sure you match up your volume and molarity of your acid on one side of the equation, volume and molarity of your base on the other side. We solve for that volume of the base. We end up with 8.22 milliliters of calcium hydroxide. Now moving on to page R68, we're starting to look at some redox, oxidation states. Okay, so 231, what is the oxidation state or oxidation number of sulfur in each of the following species? So they're identifying sulfur as the need here, but it's good practice to be able to identify all of our oxidation states. But in this case, ASF6, when we have something like fluoride, fluoride is going to be a -1. Metals typically have an oxidation state of whatever their charge is, especially if they're leading our compound. So like calcium in part B is going to be a +2, okay? We will have fluoride is not a metal, but our halogens, if they're in a binary compound like this, they're going to be -1 because that's what their natural ionic state is. So 6 fluorides in this compound mean we have a -6 oxidation state over here on the right side of our compound. So we have to figure out what will go with that -6 to make the entire compound neutral, and our sulfur will have to be a +6 in order to balance that -6 from the fluorides. So in this case, sulfur's oxidation state is a +6. So moving on to part B, we've got calcium. Calcium's a group 2 metal. It's leading our compound here, so it's a +2. We have oxygen. Oxygen is always a -2 unless it is peroxide. So H2O2, Na2O2, K2O2, when we have that kind of situation where we have a doubled positive ion and then we have a doubled oxygen with it, that's a peroxide. In that case, it's a -1 oxidation state. But that's not what we have here. We have 3 oxygens in this compound. This is a -2 oxidation state. 3 oxygens makes a total of -6. The calcium is a +2, like we talked about before. So our known pieces, -6 and +2, end up canceling down to, or netting -4, which means that our sulfur has to be +4 altogether. There are 2 of them, which means each sulfur in this case has an oxidation state of +2. K2SO3, similar situation. Part C here. K is a metal. It's leading our compound. It's just going to have its charge. It's a +1. There's 2 of them, so that would be a total of +2. The oxygens, again, are going to be a -2 because we don't have a peroxide situation. So 3 oxygens is -6. Again, 2 potassiums is a +2. So that's total of -4 between the oxygen and the potassium. So sulfur has to balance that since we have a neutral compound. So in this case, our sulfur is going to have a +4 oxidation state. This might be easier to see written out. I'm working from a PowerPoint presentation, which is a little hard to write on. So if you need help with this, please make sure that you come see me. Part D, again, oxygen is always going to be a -2 oxidation state. And since there are 3 of them, this is going to be -6. So in this case, sulfur is balancing all of that -6. So sulfur has got a +6 oxidation state. All right, part E, I'm glad this one's in here. Sulfur, pure sulfur, it's an element by itself, it's going to be 0. So when I have been saying oxygen's always a -2, unless it's a peroxide, which in that case it's -1, I really was leaving out the fact that if it's just oxygen by itself in its pure elemental form, it's going to have an oxidation state of 0. So by definition, a pure element is an oxidation state of 0. All right, last one here. F, hydrogen is a +1, oxygen is a -2. There's 4 oxygens, which is a total of -8. There's 2 hydrogens, which is a total of +2. The -8 and the +2 become -6, so the sulfur has to be +6 in this one as well. For 232, we're looking at the bromine instead. I'm going to talk through it a little bit faster, probably not pointing out quite so much. But in part A, cesium is a +1, so bromide -1. So bromine is going to have a -1 oxidation state. Part B, sodium is a +1. Each oxygen is a -2. The -6 from the oxygen plus 1 from the sodium makes a total of -5. So in this case, our bromine has a +5 oxidation state. Part C, this is not peroxide. This is let's see, bromite, I guess. Bromate would be BrO3, so this would be bromite. Our oxygens are -2. There's 2 of them. That's -4. But this is the first time we've seen this. We see a negative charge on our thing that we're trying to find an oxidation state for. So our total negative charge from oxygen is -4. We're going for a -1 as our net. So our bromine must be a +3 oxidation state in order to make that negative total. All right, bromine, pure bromine, 0. Over here, bromine, chlorine. Which one do we get? Well, the more electronegative one's going to be negative, but also when we list things, we typically list them in order of positive, negative when we do compounds. So that can help you remember that. So chlorine's going to be our -1 and bromine's going to be +1. Over here, oxygen, -2. Sodium, +1. That's a total of -1, so our bromine needs to be a +1 in order to keep a neutral compound. Okay, 233, consider the following reaction. Which reactant lost electrons? Well, if we're looking at this, if you were to split this up into an ionic equation, copper here is a 2+ charge. Copper here is a 0 charge. In order to go from a 2+ to a 0, it has to gain electrons. Iron is 0 charge here, 0 oxidation state. Over here, +2 charge. So it had to lose electrons to go from a 0 to a +2. So iron is the reactant that lost electrons for part A. For part B, which one is the oxidizing agent? Remember, oxidizing agent is causing something else to be oxidized, which means it itself is being reduced. Copper is going from a 2+ over here to a 0 over here. Sorry, I wasn't pointing earlier. I think I'm pointing, but I feel like you can't see it. So anyway, copper is going from a 2+ to a 0, which means it is being reduced, and that is our oxidizing agent for part B. Part C, which reactant was oxidized? Well, oxidized means its charge is going up. So our iron, which is going from 0 before the arrow to +2 after the arrow, is being oxidized. And if it is being oxidized, it is also the reducing agent. So iron is our answer to part D as well. So iron got a lot of attention on that problem. All right, 234. In each of these reactions, is sulfur oxidized or reduced? In order to figure that out, you have to figure out its oxidation states. In part A, it's the second element. It's going to be its ionic charge here, -2. But after the arrow, it is pure elemental form. It is 0. So going from negative 2 to 0 is going to be being oxidized. Its charge is going up or becoming more positive. Here, part B, elemental sulfur, 0. This side, it's going to have a +6 oxidation state. So 0 to +6, its charge is becoming more positive. So again, it is being oxidized. All right, H2SO4. Looking at this one, our sulfur is going to have a +6 oxidation state. On this side, it has a -2. So it was reduced big time. Sulfur was reduced in this reaction. Its charge went way down. And then part D, we've got sulfur at elemental 0, and then sulfide at -2. So it is being reduced again. Balancing those equations, I'm sure that you guys were successful on that, so I'm going to let you check that on your own if you would like to check your balancing. All right, we're going to look at the Canvas practice problems, starting with the titration problems that I wrote in Canvas. Okay, we're going with part number 1 here. Each of the following acids is going to be titrated with sodium hydroxide. Write a chemical equation for the acid-base reaction, and then a net ionic equation for each reaction. So this one, this is going to be hard for me to go over as a slide, but we've got hydrochloric acid for our first acid. This is a strong acid. When it combines with sodium hydroxide, we'll have HCl plus NaOH. It's a straight double replacement. We're going to end up with NaCl and H2O. In that reaction, everything is aqueous except for water. And so when we split things up and we cancel things that are aqueous on both sides, your net ionic equation will be H plus OH minus gives you H2O. Part B, we're working with hydrofluoric acid. Now, hydrofluoric acid is a weak acid, which means that even if I write HF aqueous, HF is going to stay associated in solution. It does not split into H plus and OH minus. So we'll remember that later. Our total chemical equation, HF plus NaOH gives you NaF plus water. Again, everything is aqueous except for the water, but the HF does not split when we create our net ionic equation. HF stays together. NaOH splits into Na plus and OH minus. On the other side of the arrow, NaF will split into Na plus and F minus. And then the H2O will stay together. So the only ion that cancels in this weak acid strong base reaction is going to be the sodium. Sodium cancels out. Your net ionic equation will be HF aqueous plus OH minus aqueous gives you F minus aqueous plus H2O liquid. All right, part C. This acid is called chloric acid. Anything with chloric, hydrochloric, chloric, perchloric, all of the chlorics are strong. So this acid will react very similarly to our reaction from part A. We just have chlorate instead of chloride, but we have HClO3 plus NaOH gives you NaClO3 plus H2O. Everything is aqueous except for water. The acid being strong does dissociate into H plus and ClO3 minus, so we will have 2 spectator ions, and your net ionic equation will be the same as part A. H plus OH minus gives you H2O. All right, this one, part D, is chlorous acid. This is going to be a weak acid and will react very similarly to our acid from part B. HClO2 plus NaOH gives you NaClO2 plus H2O. When we go for our net ionic equation, remember this acid will not dissociate. So it will be aqueous as an entire acid formula. It will not split into H plus and ClO2 minus. So our only spectator ion, once again, will be sodium. So our net ionic equation will be HClO2 aqueous plus OH minus aqueous gives you ClO2 minus aqueous and H2O liquid. Our final one here in part E, H2SO4, this is sulfuric acid. This is definitely a strong acid. We're going to work on memorizing those acids, especially next in our next book when we work with acids and bases some more. But this will completely dissociate. We're going to end up with H2SO4 plus 2 NaOH gives us Na2SO4 plus 2 H2O. And because of that dissociation, we will end up with an ionic equation of H plus OH minus gives us H2O. If you want to have 2H plus 2OH minus gives you 2H2O, great. We can cancel all those 2's and simplify that reaction to the same as our net ionic equations from parts A and C. Okay, question 2. For each titration reaction in question 1, determine the number of milliliters of NaOH needed to reach the equivalence point. Remember, equivalence point means that our hydroxide and our H plus are equivalent. We have the same amount of acid and base in our reaction. Because this base that we are, this base that we're titrating with up here is 0.1 molar. This is really great. I don't have a mouse either, so this is really fun. 0.1 molar NaOH, and all of our acids over here are 0.1 molar. All of them are 0.1 molar. This means that it will be a 1-to-1 relationship. Now, if we didn't have those exact same molarities, we would use M1V1 equals M2V2, and we would solve it. But because they are the same molarity, the molarity will always cancel, and our V2 will equal our V1. So for part A, we're going to need 20 milliliters of sodium hydroxide to neutralize. For part B, we're going to need 40. For part C, 15, D, 30, and E, 25. Okay? All right. Part 3. For each titration in reaction 1, predict the pH of the reaction at its equivalence point. Remember, when we have a strong acid with a strong base, our pH at the equivalence point will be 7 because they will neutralize completely. 7 for A, 7 for C, 7 for E, because those are strong acids. So A, C, and E are all going to have a pH of 7 at the equivalence point. When we titrate a weak acid, so B or D, with a strong base, we will end up with a basic equivalence point. So even though our acid and our base have equal volumes and we have completed our reaction, because we will have some leftover conjugate base of those weak acids, that conjugate base can literally pull hydrogen atoms or protons off of water, creating a slightly basic environment. We will learn this a lot more later, but for now, know that if you're using a strong base and a weak acid, your equivalence point pH will be basic, and then vice versa is true as well. So you could pick a 9, a 10, somewhere in there is going to be your pH at the equivalence point. Number 4, why does it matter what the pH will be at the equivalence point? Well, when we're doing an acid-base reaction, we use an indicator, and that indicator has an end point at which it changes color. You want to make sure you use an indicator that will change color in the pH range of your equivalence point. So we need to know what the equivalence point pH will be to pick the correct indicator. Number 5, make a graph of volume of NaOH added versus pH for titrations A and B. Be sure to put the endpoints in the correct volume of NaOH and the correct pH. Maintain the shape of your titration curve, and consider your acids when deciding what the starting pH should be. Well, I'm going to work with HCl first. We have strong acid, strong base. We're going to be starting with our strong acid. We're adding base. Its pH will shoot up at some point, and then it will level out again at a high pH. This is really, really hard to draw with just a finger on a touchpad. Okay, so with this, your pH down here might be like a 1 because it's a strong acid. And your pH up here might be a 12 or a 13, okay? So strong acid, strong base. We're looking at some pretty extreme, that's a 2. Okay, we're looking at some pretty extreme pHs at those endpoints. Now, if we're working with reaction B, first of all, we have to notice a couple of things. 1, in A, we were titrating 20 milliliters, which means that my vertical point, this vertical place right here, let me try to draw it right here. That should be at 20 milliliters. I'm going to try to draw another two. Okay, 20 milliliters of base was added to get to that that vertical point. Okay, if we're titrating now, we're titrating 40 milliliters of our second acid in part B. Okay, our weak acid. We have to notice a few things. Well, it's a weak acid, so its pH is going to start higher than the strong acid. Okay, it's still acidic, so maybe a 3. Okay, so we might start here. But because we're titrating twice as much volume of that acid, it will not go vertical until we get to 40 milliliters. So maybe my 40 line might be over here. Okay. So we're going to drag this out a little bit, and it's going to start to go vertical, and it will still go vertical at 40, and it's going to top out at a similar or same pH as our first titration was. That was not the greatest curve, but we're still titrating with the base. So once our acid is all gone, we'll still level out at that 12 pH. I didn't do the best job drawing that, but remember, it's going to go vertical at 40 because we are titrating twice as much volume. And man, I'm having a hard time drawing this. Okay. And then it will still level out at that same high pH because we're using the same base as our titrant. Okay, so starts out at a higher pH, ends up at the same pH at the end. Hopefully that made sense. Sorry for my difficulty scribbling. Okay, redox practice, our last little piece, and then you will be ready. I have confidence in you. Okay, so this is back to more oxidation states for this first piece. Okay, we're going to identify the element being reduced and identify the element being oxidized. We're going to label them. We're going to identify oxidizing and reducing agents. And when you remember, look for words like justify when you are taking your AP exam. When it says justify, you need to explain. And if it tells you what to use to explain, you need to make sure that you use that. Okay, so if we're looking at silver oxide, again, oxide is always a -2 unless it's in peroxide. So reminder, peroxide, H2O2, Na2O2, K2O2. Those are examples of our peroxide. We've got 2 +1 ions bonded to 2 oxides. Those oxides are not oxides, they're peroxide, and they are a -1 oxidation state. In this case, we don't have that, but I just want to make sure I keep reminding you of that because that's definitely an exception that they like to throw on the AP test. Okay, so oxygen is a -2. There are 2 silvers with the oxygen, so each silver is a +1, and on this side, silver is elemental, so we've got a 0. +1 to a 0. That is a reduction. Silver is being reduced. Because it's being reduced, it is the oxidizing agent. Automatically, our other metal is going to be the opposite in this case because oxide is going to stay our -2. Aluminum is going from a 0 to a +3, which means it is being oxidized and it is the reducing agent. Okay. Again, justifying using oxidation states, you're just going to actually write their oxidation states, and that can be used to give you your justification. Okay. All right. Number 2, use the reaction below to answer the next questions. We've got iron chloride, calcium, calcium chloride, iron. Write the net ionic equation for the reaction in question number 2. Well, if we look at this equation as it's written, the only thing that is aqueous on both sides is our chloride. So the chloride is going to be our spectator. When we write the net ionic equation, the one thing we have to make sure that we remember is that it's balanced. So when you get this, you should have 2 Fe3 plus 3 calciums, no charge, gives you 3 calcium 2 and 2 Fe, no charge. That's your net ionic equation. B, what type of reaction is it? It is a redox, but it is also a single replacement, so we have to keep those chemical equation names in our brains. C, write the reduction half reaction for the equation. Reduction half reaction for the equation. So remember, what was being reduced was our iron. You could write an equation. I'm going to try my best to write this here, but we've got Fe. There are 2 of them in the equation, but you don't necessarily have to do that. So we have an Fe2 plus. Oh, this is taking a really long time. And on the other side of the arrow, it is just an Fe. So in order to become just Fe, hopefully we remember what had to be transferred to it in order for it to do this. But if it's going from a 2 plus to a 0, it means it had to gain some negatively charged subatomic particles called electrons. And the number of electrons that it had to gain was 2. So we have to put those electrons over here on the reactant side. So Fe2 plus 2 electrons. 2s are not my friend on this touchpad. Okay, plus 2 electrons gives us Fe. That was really, really messy. Okay, write the reduction half, part D, right? The oxidation half of the reaction for the equation is going to be our calcium piece. We're going to have Ca all by its lonesome before the arrow, and then draw an arrow. We're going to get Ca2 plus. Oh, and I totally messed this up here. Iron is a 3 plus, and we're going to end up with 3 electrons, giving us iron. Okay, calcium is going to be calcium, arrow, and then we'll have Ca2 plus and 2 electrons. If you wanted to keep the balancing from our original reaction, we would end up with 2 irons, 6 electrons, and then 2 iron atoms on the right side. And we would have 3 calcium atoms, arrow, 3 calcium ions, and 6 electrons. Part E, why aren't the spectator ions included in either half reaction? Because they are not being oxidized or reduced. So the chloride doesn't change. It's not being oxidized, it's not being reduced, so it's not in either of those half reactions. Question 3, use the half reactions below for the following questions. We've got cobalt becoming CO2 plus. We've got lead 4 becoming lead. Which half reaction is oxidation and which one is reduction? The cobalt becoming CO2 plus, its charge is becoming more positive. It is an oxidation. The lead 4 plus becoming lead with no charge is a reduction. Its charge is going down to 0 from 4 plus. There's lots of ways to remember oxidation and reduction, but like Leo Ger, lose electrons is oxidation. Ger is gain electrons is reduction. So if we look at that second reaction, lead is gaining electrons, so it is a reduction, Ger. I just always think it through. Reducing is charge going down, oxidizing is the opposite. B, use the half reactions to create the net ionic equation for the overall reaction. Well, before you can add these two reactions together, you have to make sure their electrons are going to cancel. So we have to double our top reaction in order to get 4 electrons in it. And then our net ionic equation, when we add the two together, will be 2 cobalt atoms plus lead 4 plus gives you 2 cobalt ions and lead solid. And C, what is one possible spectator ion that we don't see in the half reactions or the complete net ionic equation? We have to think about a spectator ion, an ion that would be aqueous on both sides of this equation, and lead is not very soluble with very many things, so we need to think of an anion that is soluble almost always, or in this case always. Nitrate would be the great choice for this question. Nitrate is always soluble, so it's always going to be a spectator in a single or a double replacement reaction. Well, that's all I've got for you. I hope that was helpful. And again, make sure that you ask us more questions in class if you need any help with this stuff. Thanks, everyone. Bye.